Okay.
Okay, folks, this is our lab on free damped vibration experiment with a pivoted beam. This is our lab sheet we're going to use to fill in as we're going along. So we've got our pivoted beam here with a spring, and if I pluck it, it oscillates, so we've got a free oscillation. Now we've also got a paper recorder here that we can record the oscillations. We just do a quick demo of that. Which kind of is okay. Pause. Okay, so folks, on the screen there now we have also a representation of the waveform electronically. So what we've got here is a proximity sensor that's giving us the waveform. I'll go through that later, which talk to you about it. Absolutely right. Here we have the paper recorder. So we'll get a physical representation of the oscillation on the paper, and we'll have a look at that shortly. Okay, so folks, this is kind of what it looks like from the paper recorder. And here's a couple I did earlier. Okay, so what we've got here is that the feed rate of the paper is 20 millimeters per second. And we have several oscillations, and we know the speed of the paper is 20 millimeters per second. So what we do is we measure one period in millimeters, and then we convert it to seconds, and we work at the frequency. Just pause there. Okay, so what I've done is I've measured over several periods with the ruler, and you can see I've got 30 millimeters over 9 oscillations, 9 periods, 9 full cycles. The reason I measure over several ones is that my error is reduced. You can see that there 30 divided by 9 is almost 3 millimeters. If I have a ruler, my error is plus or minus 1 millimeters. So if I have a measurement of 3 millimeters for one period, my error is huge. Whereas if it's 30 millimeters, my error is still plus or minus 1 millimeters. Pause. Okay, we now introduce a damping element, which is a piston and plunger, a bit like your bicycle pump. It's an oil-filled damper. So now when we have an oscillation, the oscillations die away much quicker, and we're going to show that on the screen. Okay, so now we're showing the amplitude on the screen from the proximity sensor, and we can see that it dies away rather quickly to 0. Press play. Okay, so now we've moved the damper much further up the arm, and this increases the damping considerably. So you can see physically it shows down, and I'm going to show you now on the screen. So folks, you can see now that that oscillation almost goes to 0 pretty quickly. We're only getting about 2 or 3 oscillations. It's quite heavily damped. Yeah, okay, you can see that. Okay, so this is a shot or a frozen screen of the waveform. We can do this with the trigger function on the software here. It's not dissimilar to a pause button or a stop button on a proper oscilloscope. So you can see the oscillation is dying down, and what we're interested in finding out is how the successive amplitudes change. Okay, so you can see that one is higher and that one is higher and that one as it rolls down. So what we want to do is measure amplitude 1 and amplitude 2, or maybe in fact I'm going to go amplitude 1 and amplitude 5. Okay, so then we can determine what the damping factor is. So we've got a scale here, and because it's a ratio x1 to x2, it doesn't really matter what the scale is. Okay, so this happens to be amplitude in volts. So our x1 here would be 2.52, we'll say, and then x1, x2, x3, x4, x5, and x5 is about 1.9. So that's your typical type measurement we're going to make. Okay, so I'm going to show you some typical data from a range of experiments. So we move, and pause there a second. Okay, so what we're going to do, folks, is we will have the damper in different positions or along the beam. Okay, so we can move it up and down. Okay, the radius on the arm is which it's at. So what I'll be showing you is some typical values of our amplitude reduction for different positions of the damper as we go out along the beam. So we're going to vary our, and then we're going to see that our damping factor reduces considerably as we go out. Okay, so just one thing I meant to show you at the start, but that's the fun and games that we're having with this lab, is that this is the undamped waveform. You can see it does eventually die down, but there's very little damping involved in it. And what we can do is we can check our values for the frequency by just simply measuring the distance between those two peaks below here, because we have a time domain here, and we can simply measure what that is. Pause there. Okay, I'm going to measure this just using the screen here. So I've moved the cursor into the top of that peak, and that's giving me a reading here of 0.205 seconds. 0.205 seconds. Now I can move it over to the other peak, as you can see, and that reading is 0.369 seconds. 0.369 seconds. So now we can measure the period in time, which we'll do.